Thank you everyone for being here tonight. Tonight, I'm going to talk about the V8 engine under the hood. Okay, not that V8 engine under that hood. Yeah, okay, that's the one. The Google V8 engine powers some of the most important technologies across the web. Technologies like the Chrome web browser, Node.js, Electron, Dino, and more. But exactly what is the V8 engine? V8 is by far the most popular JavaScript engine on the market today. And I know what you're going to ask next. Okay, it's a JavaScript engine, but what does it do? The V8 engine makes all of the dynamic content you see on the web today possible. It does this by turning the JavaScript code the software developers write into machine code that can be executed by your computer. This is a fairly complicated process that has been iterated and improved on for many years. A lot of different steps are involved, and a few of the important ones even have their own names. The four main components of V8 are called Ignition, Turbofan, Liftoff, and Orinoco. I'll talk more about them a little later, but first I'm going to go through the steps of the V8 engine's conversion pipeline, and I'll elaborate on these technologies when they come up. Okay, so the first step in the V8 engine pipeline is the parser. The parser is going to take your JavaScript source code and it breaks it down into all kinds of different tokens. Things like keywords, identifiers, operators, and values. Then it's going to evaluate all the tokens and find out how they interact with each other and assemble them into an abstract syntax tree, or AST. This AST is still not something that computer hardware can understand and execute, so we need to break it down a little bit further. To do that, there are two strategies that we could choose. They are compilation and interpretation. These two strategies achieve the same goal, but in very different ways. A compiler turns source code into machine code before execution. Once compiled, the code will run very quickly. This is because the compiler has seen the entire code base and can use shortcuts to optimize execution. The downside is that it can only execute this machine code on computers that have the architecture that the compiler was written for. If you want to support multiple different architectures, you have to compile the code multiple times. An interpreter, on the other hand, turns the source code into bytecode, which is a set of predefined instructions that can be immediately executed. This process is slower since the interpreter cannot optimize anything because it hasn't seen the full code base yet. The upside is that this code can be run on any device as long as it has that interpreter installed. So which strategy does V8 use? Well, the answer is both, of course. V8 combines both techniques in a process called just-in-time compilation. Just-in-time compilation combines an initial interpreter called Ignition paired with an optimization compiler called Turbofan. After the parser constructs the AST from the source code, it continues down the V8 pipeline, which looks something like this. The AST is then delivered to Ignition, which interprets it and turns it into bytecode. This bytecode is then immediately executed, at which point our program is running, albeit inefficiently. While our code is running, Ignition is taking notes on parts of the code that could be optimized. For example, JavaScript is a dynamically typed language, so a function can use any type of data. We don't have to define it before execution. But if we keep using the same data type for a function, we can send that type feedback to Turbofan, which can compile optimized machine code to run that function instead of the inefficient bytecode. If for some reason we switch up our types later on in our function, later in the code, Turbofan is able to de-optimize that code and send it back to Ignition to be executed as bytecode again. Another situation where our optimization compiler comes in very handy is when the interpreter comes across some hot code or code that loops or otherwise uses a lot of resources. That code will then be sent to the compiler while it's still running. And as soon as the compiler has a more efficient solution, the execution threads will be hot swapped out and the more efficient code will take over. That's the basic conversion pipeline that V8 employs. Now I'm just going to review the major technologies that it uses. As I mentioned on the last slide, Ignition is a JavaScript interpreter. It turns the AST delivered from the parser and turns it into bytecode. Bytecode is not machine code though, and it still cannot be directly executed. So it's fed into the back end of Turbofan to be compiled into machine code. Although since it's bytecode, the compilation is predefined, so it goes very fast. That machine code is then immediately executed and Ignition continues on while keeping track of inefficient code and sending that feedback to Turbofan. Which brings me to Turbofan. This is our optimization compiler. It takes the feedback from Ignition and turns the bytecode into optimized machine code by making assumptions based on the data types that has been seeded. If necessary, it can also de-optimize machine code back into bytecode and sends it back to Ignition. Currently, Turbofan can compile machine code for 9 different computer architectures, which if you had to do it all one by one would take quite a long time. The next 2 technologies weren't in the previous diagram because they're not part of the JavaScript conversion pipeline, but they are a part of V8, so I'll briefly go over them. Liftoff is a baseline compiler that only comes into play when the engine encounters WebAssembly code. WebAssembly is designed to run very reliably, so it's compiled ahead of execution time, but that can make the initial execution time kind of slow. So Liftoff fixes that by compiling machine code as fast as possible with no regard for efficiency at all. The code is then executed, but while it's running, Turbofan is compiling the WebAssembly into optimized machine code. When it has a more efficient version, the threads are hot swapped and the more efficient code will take over again. The last technology on the list is Orinoco, the garbage collector. This is a very important part of V8 because it allows the developer to write code without having to manually manage memory allocation. So when memory is no longer needed, it's cleared out by Orinoco, but there are also some very clever optimizations. If an object in memory survives garbage collection the first time, it's put on a list, which is not checked as often. This allows the garbage collector to save computer resources and not slow anything down. Also, any new objects that are first put on that list are flagged so that they don't check them the next time, just a further optimization. That's the basic operation of the V8 JavaScript engine. If you'd like to know more, I have included several links to some resources that I used while creating this presentation. And if you have any questions, I can take some now, or you can feel free to email me or contact me on LinkedIn. Thank you very much for your attention. Are there any questions?